Okay, good evening. So this is 33rd lecture, and today we will talk about yeah. So today we will talk about viscous flow in ducts. Okay, so we completed our discussion on dimensional analysis in the previous lecture. So this is a new topic. So basically, the flow of viscous fluids through ducts is a very popular topic, and it has plenty of applications in many engineering and industrial processes. Okay, so if you talk about any process industry, you will be finding, for example, if you talk about the thermal power plant. Okay, so in case of a thermal power plant, you are having a boiler, you are having a turbine, then you have condenser, you have pump, and if you have to transfer the working fluid from one component to other component, then you are having number of pipe arrangements connected. Okay, moreover, within the individual components, for example, if you talk about a boiler or if you talk about a condenser, there also you are having multiple number of tubes arranged through which your actually working fluid passes, and it undergoes through different heat exchange processes. Okay, similar to that, if you talk about any chemical industry where group of reactants are put inside a reactor, then these flows along the length of the reactor, and ultimately these gives you some final product, and these products, if are in the form of fluids, then ultimately these are transferred from one location to other location. Okay, similarly you have another important example. You see, we are using nowadays gas and oils as the important fuels for obtaining energy for different purposes. For example, for running our automobiles, for cooking uh, at our home. So we are having long oil and natural gas pipelines through which actually crude oil or gas flows from refineries to the I first from uh, oil exploration sites to refineries, and then from refineries to the actual application sites. Okay, so we can say that the flow of fluids through ducts is actually one very important fundamental area which has applications almost in every area of engineering and other industrial applications. Okay, so typically whenever the flow takes place through ducts, then we are having some interesting flow features. Okay, so one important point is here, as the title of the lecture itself says, viscous fluids in ducts. So it means we have to consider viscosity of the fluid. Okay, and once we are considering the viscosity of the fluid into account, then within the pipe we can have two types of flow situations. So one typical situation is referred to as laminar flow, and other is called as turbulent flow. Okay, so to explain you the difference between the laminar and turbulent flow, one photograph is shown over here. So you can see that in the first photograph, our flow rate of water which is coming out of this pipe is actually small. Okay, so here flow rate is small. So once flow rate is small, whenever this water is coming out of the pipe, it is having some smooth profile. Okay, and it is not having any disturbances present within it, and if any disturbance arises, that also dampens during the flow. Okay, so this is called as laminar flow. Then you can see that if you have high flow rate, okay, so at high flow rate you will be finding some sort of disturbances within the flow. Okay, and if at same flow rate, if you adjust the shutter speed of the camera such that you have the small exposure time, then you can even find you can even capture these disturbances on the surface of the jet. So you can see how wavy is the profile, and within this also you have some sort of disturbances here in these zones. Okay, so this type of flow situations where our flow streamlines and path lines are not regular, these are irregular and chaotic, this is called as nothing but a turbulent flow. Okay, so to give you some idea visually, this is one video. So you can see in this video, initially when flow rate is small, then you can see this particular black colored whatever this tracer we have injected, this tracer is actually smooth. When flow rate is increasing, then this tracer has started giving some perturbation, and these perturbations are actually keep on growing when the flow rate is increased further. Is this one clear? So now when the flow rate is being increased, so in the later portions we can see that this has become nothing but a turbulent flow situation. And initially when the tracer was almost straight, corresponding to that the flow profile was smooth and our condition was nothing but of laminar flow. Okay, and in between the laminar and the turbulent flow, to some portion we have seen that there were certain disturbances, but these disturbances were not huge. Okay, and these were kind of intermittent, not continuous. So that particular regime is called as actually transition regime from laminar to turbulent flow. Is this point clear? Okay, so now you can see basically how turbulent flows takes place within a pipe. So these are some experimental photographs in a transparent pipe which are captured for turbulent flow conditions. So you can see this, the part A and part B are corresponding to the near the inlet portion of the pipe. So you can see near the inlet portion of the pipe, this black colored portion is nothing but kind of, I can say that, laminar zone, and in this particular zone my flow is actually smooth, and outside this you can see the lot of surface irregularities here, some sort of rotating and chaotic interfacial structures. These are chaotic structures, these are nothing but the turbulent zones. Okay, and then further you can see that when you are moving away from the entry of the pipe, then these turbulent zones are becoming more chaotic, and this is even a more complex chaotic portion. Okay, and once you go far downstream of the pipe, then you will be finding some sort of conical portion is created, and in this conical portion you have actually huge amount of formation of small irregular chaotic structures which are called as turbulent eddies. Okay, so this type of flow is typically called as turbulent flow. Okay, now here comes important aspect. So when we are saying that our flow is changing from laminar to turbulent, so we should have some quantitative criteria which will be actually representing the transition from laminar flow to turbulent flow. And of course during the transition also flow is chaotic, but that is this particular chaotic portion is not having any continuous chaoticness. Okay, so now to understand this, basically if you talk about in the early days we were not having very high end or sensitive instruments which can actually capture these small turbulent fluctuations. Okay, so it was extremely difficult to capture the small turbulence turbulent fluctuations. So turbulent fluctuations we were able to capture somewhere after 1930s when actually the sensitivity and the sophistication of these instruments have improved. Okay, before that, whatever the turbulent analysis we have observed, the major idea was to actually rely on changes in the broader macroscopic or average parameters, and once the average parameters are actually changing, then we can say that okay, transition has happened. Okay, so to clearly indicate the difference between laminar and turbulent flow, I can show you that in case of laminar flow, if I consider a one-dimensional flow, then my path line of the flow will look something like this. So if say this is my x dimension, this is y coordinate, and this is z. So if along the x direction I consider my flow, then my path line of the flow will be something like this. If I talk about that my flow is laminar. Okay. So for this type of flow field, if I have to specify the velocity field, my velocity vector will be simply nothing but u times I cap. Okay. And I will not be having any other component of the velocity in y and z direction. Is this point clear? On contrary, if I talk about turbulent flow, in case of turbulent flow, my path line of the flow will not be a straight line, but I will be having some random patterns within the flow path line. Okay, so this is nothing but a typical turbulent flow path line. So fluid particle is not moving in a straight and smooth manner, rather it is having a significant number of flow fluctuations. Okay, so now in this case what will be happening, particularly in case of turbulent flow, okay, so particularly in case of turbulent flow, I will be finding that the mean flow or bulk flow of the particle is in x direction, but along with the mean flow or bulk flow, it is also having some interface oscillations. So it is also having some oscillatory or irregular path. Okay, so if I have to specify the velocity vector over here, velocity vector will not be constituting only a single component, it will be having other components also, but major bulk mean flow component will be in the x direction. So I can specify the velocity field for this type of turbulent flow as nothing but u bar plus u dash in I direction plus v dash in j direction plus w dash in k direction. Okay, so over here what I am trying to say is basically my u bar represents the mean flow velocity field. This is nothing but mean flow velocity component, and u dash is fluctuating component in x direction. Okay, similarly v dash is fluctuating component in y direction, and w dash is fluctuating component in z direction. Is this point clear? Okay, so I have my mean flow of the fluid in x direction. Okay, that's why my mean velocity in velocity field is only appearing in the x component. Okay, on contrary, because turbulent flow is nothing but chaotic, having irregular structures, so because of this irregularities and chaotic nature of the flow, when a fluid particle is majorly moving in the bulk x direction, it will also have some irregular motions along the y and z direction. So it can have irregular motion in x direction, fluctuating motion in x direction, as well as in y and z directions. Okay, so that is the reason I am writing this u dash, v dash and w dash as the additional components of fluctuations in my flow field. Okay, so one simple understanding from this point we can see is that whenever we will be talking about the turbulent flow, it is having inherent three-dimensional nature, because turbulent fluctuations are present in all the three directions. Okay, on contrary, now you may got some confusion that whenever defining the steady versus unsteady flows, I cannot say whether my flow will be turbulent flow will be steady or unsteady. Okay, so this confusion will be coming to our mind. But one important point we can say over here, if my U average is not changing with time. Okay, if U average is not changing with time, then I can typically say that my turbulent flow is steady for mean velocity. Fine. So turbulent flow can be defined steady only in terms of the mean parameter if mean parameter is not actually changing with time. On contrary, because it will be always having a fluctuating component, these will always keep on changing with time. So in terms of fluctuating components, I cannot say that my turbulent flow will be steady. Is this one clear? Okay. Now, as I told you that in the initial days we were not having sophisticated instruments, sensitivity of the instruments were very low. So because of that, we could not actually quantify the fluctuating components in the flow field. So very initial studies were only able to classify the flow regimes just based on the significant changes in the mean parameters. Okay. So one such experiment was done long back in 1839, and this experiment was done by Hagen, and in his experiments Hagen has taken actually smooth pipe, and through this smooth pipe he has allowed the fluid to flow at different flow rates. Okay, and once the fluid was flowing at different flow rates, or I can say at different flow velocities, then he used the measurement of the pressure at these 2 points. Say at this point pressure is P2, at this point pressure is P1. So delta P was considered as the pressure drop P1 minus P2, and this delta P was plotted as function of the velocity of the flow. Okay. So in his experiment it was observed that whenever he plotted the average velocity of the flow as function of pressure drop, then this pressure drop was proportional to velocity up to some point, and after this point this curve was actually this curve is not a straight line, but it is taking some other shape of the curve, and in this particular regime delta P was proportional to V power 1.75. Okay, so this particular point at which, so you can see in this zone you have straight line, okay, and above than this your curve is following 1.75, but this dashed line shows some deviation from the actual data in this region. So this particular region can be called as nothing but the transition region. Okay, and in the laminar regime, so one important conclusion we have got from here, that for Newtonian fluids, if fluid is flowing through a straight and smooth and a circular pipe. Okay, so this curve is for straight, smooth and circular pipe. Okay, so if fluid is flowing through a circular pipe for Newtonian fluid, in that case what we will be having? We will be having nothing but pressure drop proportional to velocity if flow is laminar. Okay, but if flow is turbulent, then my pressure drop will be proportional to mean flow velocity raised to power 1.75. Okay, so this typical point at which the transition has started, its Reynolds number based on the diameter of the pipe. If I consider diameter of the pipe as length scale in defining the Reynolds number, then this value was nearly equal to 2300. Okay, and the point from where we were seeing that complete turbulent regime is actually being followed, this Reynolds number is close to 10 to power 4, 10,000. Okay, so for smooth straight circular pipes, if Reynolds number is less than 2300, then we can say that our flow will be laminar. If it is greater than 10,000, then we can say that flow is turbulent, and if our flow is in between 2300 to 10,000, then flow will be nothing but in the transition region. Is this point clear? Okay, and all this entire curve you can clearly see over here. While we have actually obtained this curve, only two parameters were used. First parameter is average velocity of the fluid, and second parameter is pressure drop. So there is no inclusion of the fluctuating components. So only just based on the trend of the this bulk flow, this was actually obtained. Okay, and typically Hagen has mathematically also expressed this argument that delta P is equal to some constant into flow rate times radius of the pipe by 4 plus entrance effect. So basically, whenever he considered this particular pressure drop estimation, he could not find that what is the value of this constant. He has taken some arbitrary constant over here. Later on, whenever we will be doing the theoretical analysis, we will be coming to know that this constant is nothing but including the major effect which is coming because of the viscosity. Okay, Q is discharge or flow rate, and this R is nothing but our radius of the pipe. And entrance effect, what it does, why entrance effect is to be considered separately, that also I will be explaining you now. Okay, and in his major analysis, pressure drop was proportional to flow rate only. So that is the only thing he could know at that time. But when he saw that he is having some deviation in his data, then he simply said that there exist two different regimes based on which our pressure drop relation is changing, but what does these regimes fundamentally do, that he was not very clear at that point of time. Okay, so to show you that how disturbances travel in different regimes, this is one simple depiction of velocity of x component of the flow as function of time. So you can see that in this case here a small disturbance has induced into the flow at this time. So if this small disturbance is induced and Reynolds number is quite less than 2300 in the laminar regime, we will be finding that with the subsequent passage of time, this disturbance will be actually dampening the flow. On contrary, if you are having transition regime, so in case of transition regime, you will be having some significant disturbances, but of course these disturbances will not be continuous with the time. These will appear at certain time instants. On contrary, if you are having the turbulent flow regime, then you will be having continuous disturbance in your velocity field when you are measuring velocity field at any point as a function of time. So of course, in this thing, if you draw one average data of all this, that will be considered as u bar, and at any instant whatever the deviation from u bar is there, that is your fluctuating component u dash. Okay, is this point clear? So this is about the transition and how in the initial days, just based on the data of mean parameter, these two regimes were actually separated. Okay, now if I talk about the entrance effects, so one important point we have got from here is that we have to consider some entrance effects. Okay, so to study the entrance region, what we can do is, I can consider, say this is my circular duct. Okay, from outside fluid is entering at uniform velocity into this. So when the fluid will be just reaching the walls of this surface, what will be happening? Because of the viscosity of the fluid and the no slip condition, when these will be acting together, I will be finding the growth of boundary layer over here, formation of boundary layer. So I will be finding that one boundary layer of zero thickness is at the starting point. As I keep on increasing, then this boundary layer thickness will keep on actually growing. Okay. Similarly, from other side of the surface also boundary layer will keep on grow, and this will continue till both the layers are actually joining together and merging at the center of the pipe. Okay. Now, one interesting phenomenon we will be observing that if I plot velocity profile at this location, then in this region what will be happening? Here I have no slip condition. So because of the no slip condition, I will be having zero velocity at these 2 points. Okay. At these 2 points I will be having zero velocity. And when I will be moving towards the boundary layer, this velocity will keep on increasing, and within this portion which is away from the boundary layer, my value of velocity will be uniform. Okay. So here I will be having the fixed value of the velocity. So my velocity vector will be something like this. Is this one clear? Now, if I plot velocity vector at some other point, then I will be finding now this more zone is actually influenced by the viscous regime, and then I have very less portion in which I have no effect of viscosity. Okay. And as I move on along the length of the pipe, the velocity in this central zone, in this particular zone, will keep on increasing. Now, can any one of you tell me why velocity will be increasing in this zone? If I consider my fluid is incompressible and flow is steady, so if fluid is incompressible and flow is steady, then at each and every cross section I must have the same volumetric flow rate. Okay. Now you can see that outside I was having some average velocity. Inside, when I have come in this boundary layer zone, my velocity has gone below the average velocity. So if I have to keep the average velocity same everywhere, because my cross-sectional area is not changing, cross-sectional area is fixed at each and every location. Okay. So velocity in the central portion must increase, then only I will be able to keep the continuity balance. Okay. Is this point clear? So that's why velocity in the central zone actually must increase. Point is clear? I will be finding that this process of increase in velocity at the center will keep on continuing till the point both boundary layers are actually merging together, and at this point I will be finding a unified velocity profile that is having highest velocity at the center, and we have change in velocity along the decrease in velocity as we move away from the center. Okay. And this process, after this point I will be finding if at any other location I measure the velocity profile will be same. Okay. And while we discussed the applications of Navier-Stokes equation in cylindrical coordinate system, already we have seen that for pipe flow this velocity profile is nothing but having what type of nature? Parabolic nature for fully developed flow condition. So after this point, when my velocity field is actually not changing with x direction, if I consider this length to be nothing but my x direction, and along the, so here if I fix my coordinate system, this is my x direction and this is my r direction. So along the radial direction I am having variation of velocity, but the point after which, so here you can see, if I have to write down velocity field at this point, then velocity is nothing but function of both r and x, because with r it is changing, but with x also it is actually growing. Okay. At the center portion velocity magnitude is increasing as we are moving along the length, So that's why in this zone, velocity is function of both r and x. But after this point, if you plot velocity at any x location, you will be having the same velocity profile. So it means that after this point, velocity is only a function of r. Is this point clear? So if someone asks you that when we can ensure that flow has fully developed, so we can simply say that the point up to which there is variation of velocity in both radial and the axial directions in a pipe, that particular region is to be called as the entrance region. Okay, and away from this region where my velocity field is only a function of radial direction, that is nothing but my fully developed condition. Is this point clear? Is this point clear? Okay, so say this region is called as entrance region, or because over here we are not talking about heat transfer, only we are talking about the fluid flow, so this region can also be called as hydrodynamic entrance region. Hydrodynamic entrance region. Because if you have heat transfer involved, then you will be having the development of temperature profile and you can have thermal entrance region also. So that's why this entrance region is many times, whenever we are only talking about the momentum component, we also call it as hydrodynamic entrance region. Okay, let me consider that LE is the length of the entrance region. Okay, so if my flow is laminar, what is the meaning of flow is laminar? Reynolds number of the flow, when Reynolds number is calculated based on diameter of the pipe, that has to be less than equal to 2300. Okay, so if this condition is satisfied, then entrance length divided by diameter of pipe is nearly equal to 0.06 times of Reynolds number. Okay, so because in the entrance region we have multiple things. You can see this outside zone is nothing but the viscous dominant region. Okay, and this inside zone where boundary layer is not there and velocity profile is almost constant and independent of the viscosity, this region is nothing but inviscid region. Is this point clear? So in the entrance region, actually I have the combination of multiple regions. I have viscous dominant region as well as the inviscid region. So theoretical analysis of this particular region is actually complex. So from considering some semi-empirical analysis, this particular entrance length when scaled with diameter of pipe, it is found to be close to 0.06 times of Reynolds number of the pipe. Okay. So typically for a circular pipe, if you consider that you are reaching the critical condition of Reynolds number, then corresponding to critical condition of Reynolds number of 2300, your LE will be how much? 0.06 into 2300 is how much? Please calculate and tell me how much it is. 2300 into 0.06. What is the value? 138. So 138 times of D. So it means that maximum value up to which entry length can be 138 times of diameter of the pipe if our Reynolds number is equal to the critical Reynolds number. Okay. And on the other hand, if I talk about turbulent flow, then for turbulent flow, this entry length by diameter is nearly equal to 4.4 times of Reynolds number based on diameter power 1 by 6. So this is the some approximate estimate. If my Reynolds number of flow is large, then of course within the pipe I will be having turbulent flow. Okay, and to reach the turbulent flow to fully developed condition, this will be the entrance length. Is this point clear? Okay. Now one important point I would like to highlight over here, there are certain conditions for which we can neglect our entrance region, and there are certain conditions where entrance region is actually desired. Okay. How? Let me explain to you. So if you want to plot your pressure drop or wall shear stress as function of the length of the pipe, so this is nothing but length of the pipe, you will be finding that this wall shear stress and pressure drop after this point will be following nothing but a straight line relation with the length. Okay, so it will be moving in a straight line fashion. But before this, because you have more viscous, why after this it will be a straight line? Because after this point your velocity profile has become constant. Okay, so let me put only pressure over here. Okay, so after this point your velocity profile has become constant, so because of this your wall shear stress will be constant. Okay, so if wall shear stress is constant, majorly pressure drop is caused by the wall shear stress that we will be seeing in the subsequent discussion. Okay, so majorly as pressure drop is caused by the wall shear stress, and what we are doing after this point only, we are increasing the length. So viscous effect is constant, but length we are increasing linearly. That's why pressure will be forming a straight line. Okay, but before this we will be finding some non-linear variation of the pressure in this region. So one clear idea is that, and if I have to plot shear stress by some other line, so let me represent this P with red color, and if I represent wall shear stress with blue color, then wall shear stress will also be having similar variation, that it is having some huge value in the starting and then it is decreasing, and after this point it will reach to a constant value in the fully developed flow design. Okay, is this point clear? Because after this point velocity profile is actually becoming uniform, it is not changing. So after this point I will be having the smooth, I will be having the constant value of wall shear stress. On contrary, if I see pressure will be having linear variation. But before this, in the entrance design, we will be having non-linear variation, and because viscosity has suddenly started growing the boundary layer, so in the initial portion we will be having the boundary layer thickness is small. So if boundary layer thickness is small, so gradient of the velocity field will be more. So because of high gradient of the velocity field in the entrance region, I will be having very high value of the wall shear stress as well as the pressure. Okay, so because of that, my interest is to have smaller value of the entrance region. Is this point clear? If you have, say, pumping applications where you want to transfer water or any other liquid from one location to other location. Okay, so in the pumping application you have to invest certain amount of energy in order to overcome the wall shear stress or the pressure drop, then only your fluid will be moving from one location to other location. Okay, so to have efficient pumping operation so that pump consumes less power, our major interest is that we should have smaller entrance region. Okay, so if your pipeline is very long, if length of the pipe, L is length of the pipe, if L by D is very large in comparison to entrance length by D, in that case, in my previous formulation where I explained you this formula delta P equal to constant Q by R4 plus entrance region, their effect of entrance region can be neglected. Is this point clear? Effect of entrance region can be neglected. But if L by D is comparable to LE by D, then of course the developed region and the entrance region we have to separately resolve, and we have to consider the contribution of entrance region also in estimation of our pressure drop and wall shear stress. Is this point clear? There are certain applications where entrance region is desirable. Can you tell me any application where you think entrance effect is desirable? Where do you think entrance effect is desirable? Short length pipe. Okay. So basically, if you talk about, say, testing of aeroplane structures in the wind tunnel. Okay. Have you heard of wind tunnel testing? Say if you talk about testing of aeroplane. So as I told you that we need not to make the full scale prototype. We can make a small model of the aerofoil, and then we can put it inside some flow duct where we can give very high flow rate, which can meet the flow conditions identical to our actual situation of the airfoil. Okay. So in this design, what basically happens, the actual conditions are such that flow velocity for aerofoil flow are so high that our approximation of inviscid flow is suitable. Okay, because Reynolds number is extremely high. Okay, so that's why if I want to make a commensurate wind tunnel model, say this is my wind tunnel, this is a duct through which my flow of fluid is happening. Okay, and if I have put now prototype of aerofoil inside this, so whenever my velocity is coming over this aerofoil, I should have average uniform velocity across the aerofoil in this particular region. Okay, so in this region, if my boundary layer has started growing from this point, I wanted to have my boundary layer thickness to be very small so that I have uniform velocity present at the core of the flow while it is crossing the surface of the airfoil to make the situations identical to our physical scenario. Okay, so this is one important application. Whenever you see the design of wind tunnel, then typically the length of the wind tunnel is made very small in comparison to entrance length, so that we have significant inviscid portion within the flow field which can provide us uniform velocity over the structure which we want to test. Is this point clear? So this is one important application where entrance effect is actually desirable. Okay. Now let's talk about how pressure drop can be related to wall shear stress. So pressure drop measurement in a point, in a pipe. So typically I told you that in 1839, whatever experiments Hagen has done, at that time he was not very much confident about the actual set of parameters which were controlling the pressure drop, but he had given some constant times Q by R4 as the formulation, based on which we were able to get some idea. Okay, but now we have enough theories developed so that we can find out the exact formulation of the pressure drop. Okay, so to do so, what we will do, we will consider that, say I have a pipe of constant diameter. Let's consider the diameter of the pipe is D and radius of the pipe is R. Okay. Say this is location number 1 and this is location number 2. Now in between this pipe I don't have any energy dissipation and energy consuming device. Okay, so I can apply the Bernoulli equation for this pipe. Okay, so Bernoulli equation will be P1 by rho g plus, say gravity is acting in this direction and it is making some angle phi with the horizontal direction. So P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. This will be applicable only if we have the inviscid fluid. But if viscosity of the fluid is also coming into picture, then of course from this point to this point we will be having some losses. So I must add some head loss over here. Okay, and this head loss is coming because of the, this is coming due to viscosity of the fluid. Is this point clear? All are clear with this idea? Okay, so now if I calculate HF, then head loss is nothing but equal to P1 minus P2 by rho g plus V1 square minus V2 square by 2g plus Z2 minus Z1. Okay, and ultimately HF has become equal to delta P by rho g. P1 minus P2 is delta P. If pipe is of constant cross section and I have incompressible flow, then V1 will be equal to V2. Okay, so this will cancel out and this I will be getting as delta. Is this point clear? All are clear with this idea? Now let's consider that along the length of the pipe I have nothing but x direction. If x direction is along the length of the pipe. If, and say pipe is having length L between points 1 and 2. Okay, and say here wall shear stress is tau W. Fine. And if I consider that my flow is fully developed, if flow is fully developed, then wall shear stress will be having same value everywhere. Okay, so it will be having the uniform value for fully developed flow conditions. So now if I write my momentum equation along x direction, what will be momentum equation along x direction? Sum of all forces in x direction is equal to mass flow rate of the fluid times V2 minus V1. Okay, V2 and V1 are same. So sum of all forces in x direction has to be equal to 0. While I will be considering sum of the forces, pressure force plus viscous force plus body force, that has to be equal to 0. Okay, so if you consider this flow from left to right, then of course the pressure acting on the left side will be more, P1 will be more than P2. Okay, if delta P is nothing but P1 minus P2, then my pressure force will become simply delta P times area. Area is pi r square. Is this one clear? So for this piece of fluid element, delta P into pi r square will be my pressure force. What about shear force? Now because this pressure was more, this pressure was less, that's why pressure force, direction of pressure force is towards positive x direction. Okay, so I have kept it positive. If you see the direction of wall shear stress, it is acting in the negative x direction. It is parallel to negative x direction. So that's why my viscous force will be wall shear stress times area. Can you tell me what will be the area over here? On which area this wall shear stress is acting? What will be area for this? 2 pi RL, correct. So tau into 2 pi r is making circumference and it is acting over the entire length. So 2 pi RL is the area. Okay. Plus I will be having some body force. So rho times And if G is this, then of course G is acting at certain angle. So in the direction of the pipe, I will be having component as G sine phi. Okay. So I will be considering rho G sine phi times volume. What will be volume? Pi r square L. This is the cylindrical pipe. Pi r square L equal to 0. Okay. Now from here, one important thing you can see from the geometry, this angle is phi and this vertical distance will be nothing but, this is Z1 location, this is Z2 location. So vertical distance is delta Z. Okay. And this length of the pipe is L. So I can say that delta Z is equal to L sine phi. So L sine phi I can replace with L. Okay. So ultimately I will be getting that delta P into pi r square minus tau W into 2 pi RL plus rho G delta Z into pi r square equal to 0. Okay. Now what I will do, I will divide throughout by pi r square. So I will be getting delta P minus tau W, 2 tau W, 1 pi will cancel into L by R. Okay. Plus rho G into delta Z equal to 0. Okay. Now my interest is to calculate head loss. And head loss from the Bernoulli's equation I have come to know is nothing but equal to delta P by rho G plus delta Z. So I must write this equation in the similar way. So if I write delta P by rho G plus delta Z, then it becomes equal to 2 tau delta tau W L by R, and I will be having one rho G term with it. Okay. So from this I can simply say that whatever the head loss I will be having in the pipe between 2 points, that head loss is nothing but dependent upon wall shear stress. Okay. So what is the important conclusion? The important conclusion is that for laminar flow conditions, this length head loss is nothing but proportional to length of the pipe. Okay. And if I write it in terms of diameter, then HF will be equal to 4 times tau W into L by rho G D. Fine. Up to this point, is it clear? Okay. Now what I need to do is, I need to substitute over here the value of velocity field so that I can calculate tau W. Okay. Now for laminar flow in a pipe, I know that U is equal to U max times 1 minus small r square by capital R square. Already we have derived this. Okay. And if I define U average is nothing but equal to U max by 2. Is this point clear? What was U average? U max by 2. So I can write this velocity profile as U as function of R is nothing but equal to 2 times U average into 1 minus R square by capital R square. Okay. So from here, if I have to calculate wall shear stress, then wall shear stress is nothing but mu times modulus of du by dr at R equal to capital R. Fine. So this will become mu times du by dr will become 2 U average into mod of this will become 2 times R, and this R I can replace with capital R. So from here my wall shear stress is nothing but mu times 4 mu times U average by R. Is this one clear? So if I substitute back this value of wall shear stress into this head loss relation, what I will be getting? Please tell me. HF is equal to 4L by rho GD okay, 4L by rho GD into tau W. What is tau W? 4 mu U average by R, and this R also I can write as D by 2, so D into 2. Fine. So ultimately my head loss in a pipe has become equal to 32 mu L U average upon rho G D square. Okay. So the important conclusion is that whatever Hagen has experimentally observed, we are able to see the same thing theoretically. For laminar fully developed flow condition, I can see that my HF is directly proportional to A average, where HF is nothing but our pressure drop. Okay, head loss, and that is identical to pressure drop plus potential head. So if my pipe is horizontal, then it will be simply equal to pressure drop. Okay, so pressure drop for a laminar flow is directly proportional to U average, and at the same point of time, HF is also directly proportional to length of the pipe. Okay, HF is also directly proportional to length of the pipe. Probably I forgot to include it in the previous relation. This was also experimentally concluded that okay, that was on slide. Yeah, this. Okay, so HF is also directly proportional to L. Now we have some more generic correlation for head loss calculation, which are yes please, which are applicable for both laminar and turbulent flow. Okay, so I will discuss that part in the next class.